think about it, that I have two boxes and I am placing both of them in one of the box. Nothing else is allowed, no other freedom. If you have n1 plus n2 plus h bar omega, if you set E is equal to 2h bar omega, then this essentially means that you have twice h bar omega, and n1 plus n2 is 2h bar omega minus h bar omega divided by h bar omega, that is 1. So effectively now you have to figure out the combination of n1 and n2 which will give you this total energy 2h bar omega. So one possibility is 0 and 1, right? So therefore this is like having two boxes in which you place one of the particles in this box and no particles in this box. In this particular case, this is a direct contrast, because in this particular case what you had was you were not allowed to put anything in this. So effectively, as if even though you have two boxes, you have 0 particles to play with, right? What about the case when E is equal to 3h bar omega? So you have n1 plus n2 is going to be 3h bar omega minus h bar omega, and we can bring this h bar omega here and you will have 2. So n1 plus n2 is going to be 2. That means I have n1 is equal to 0, n2 is going to be n1 equal to 0 gives me half h bar omega, and I have to take it to 3h bar omega minus half h bar omega, so that is going to be 5 by 2h bar omega. So I have to place n2 in a level where I have the energy is going to be 5 by 2h bar omega, and that happens when n2 is equal to 2. What happens when n1 is equal to 1? This gives me 3/2 h bar omega, and I need another 3/2 h bar omega, right? So that n2 can also be 1, which is obvious because n1 plus n2 has to be 1. And then finally I have n1 is equal to 2 and I have n2 is equal to 0. So as if I have now two boxes, I am placing 0 particles in this box and both of them are over here, and here the configuration is this, and here the configuration is this. So I hope the general idea is clear to you now. So going back to the general case where I had E is equal to sum over I Ni plus half h bar times omega, which gives me sum over I Ni plus n by 2 times h bar of omega. So that this h bar omega minus n by 2 is going to be sum over I Ni, and clearly this sum over I, which is the sum over the occupation numbers, is going to be m, an integer. So I have m is equal to E over h bar omega minus n by 2. Now the idea is with n particles, so the entropy or the total number of microstates is omega is going to be a function of E, m and n. Idea is, now the interpretation is, as we have seen in the earlier examples, if you look over here, then 2 boxes means 2 particles. Sorry, the other way around, 2 particles, n1 and n2, 2 boxes. This quantity, which is identical to m, is 0, means no particle. You have no particles to play with. They have to be there in that box when you have this case. In this case, m is equal to 1. This is equal to your m, and you see that n1, n2 either has a combination 0 and 1 or 1, 0. That is also a valid thing, in which you place one of them here, the other one here. It is like 2 boxes, and you are just putting 1 particle either in this box, in this box. So there are 2 possible microstates. 2 possible microstates here. And in this case, as we have seen in detail, where m, the value of m was 2, there are 3 possible microstates. So the general idea is that this is now interpreted as m particles, and this is now interpreted as n boxes. Therefore, it's like you have n boxes and you have m particles. Well, you are thinking about particles, you can think about m marbles also, which you want to put them in the boxes. And this effectively means that n boxes means the end of these things are fixed. So you have n minus 1 partitions. So total of m plus n minus 1 objects. And for this, all possible arrangements that are possible are m plus n minus 1 factorial. But then you see, if you interchange this partition with this one, you are doing nothing. Nothing changes. Similarly, if you have placed a particle over here and if you have placed a particle in this box, if you interchange these particles, you do not get a new microstate. So clearly this is an overcounting. And the overcounting is exactly given by m factorial, because you can interchange between the particles and that is not going to give you anything else new. And you can interchange between the partitions, that is also not going to give you anything new. Therefore, the total number of microstates m, n is going to be this. So now, when we have this expression for the total number of microstates, we want to write down the entropy of the system as Kb ln of omega m, n, which essentially means that this is Kb ln of m plus n minus 1 factorial minus ln of m factorial minus ln of n minus 1 factorial. So if I now use a Stirling's approximation, if you recall the Stirling approximation, essentially approximates log of a factorial and factorial for large enough n as n ln n minus n. We write down this as Kb m plus n minus 1 ln m plus n minus 1 minus m plus n minus 1 minus m ln m plus m. Don't make the mistakes with the signs. And then you have minus n minus 1 ln of n minus 1 plus n minus 1. Look at this expression carefully and you see that this plus and this plus gives you a plus m plus n minus 1. So this factor now cancels with this factor, and you have S is equal to Kb m plus n minus 1 ln of m plus n minus 1 minus m ln m minus n minus 1 ln n minus 1. This is the entropy of the system. To proceed further, we note the thermodynamic relation del S del E n held fixed is 1 by T. Now this, although it looks very complicated, this expression for the entropy looks complicated, and taking derivative might be very cumbersome. One can simplify this just writing del S del M n held constant times del M del E n held constant. Recall that m is going to be e over h bar minus n over 2. So that del m del e gives you n held constant, gives you just 1 over h bar omega. And you have del s del m n held constant 1 over h bar omega. So that you have 1 over h bar, 1 by t is equal to 1 over h bar omega del m of Kb m plus n minus 1 ln of m plus n minus 1 minus m ln m minus n minus 1 ln of n minus 1. Kb comes outside and sits on top of h bar omega. Kb divided by h bar omega, and if you take the derivative of the first term, you are going to get ln m plus n minus 1 plus m plus n minus 1. Derivative of the log is going to give you 1 by m plus n minus 1, and similarly you are going to get ln of m minus m divided by m. So that you see this expression, this term is 1, this term is 1, which cancels with each other because both of them have opposite signs. You have ln m plus n minus 1 divided by m. This part I am going to recast by writing h bar omega over kbt is going to be ln of 1 plus n minus 1 over m. Now, since we are in the thermodynamic limit such that n is very large, this is going to be approximated as ln 1 plus n over m. And this implies that ln 1 plus n over m is going to be e to the power h bar omega over kbt. So that n over m is going to be e to the power h bar omega over kbt minus 1. Now, E, where did we write that? We take this expression. E is going to be m plus n by 2 times h bar of omega. If we take n constant common and outside, this becomes half plus m by n. So that the energy is n h bar omega half plus m by n follows from this equation is 1 over e to the power h bar omega over kBt minus 1. So that I have 1 over e to the power h bar omega over kBt minus 1. Right? Now, the question is, I want to cross-check and validate my result. So the best way to check it, first thing that you check is the classical limit. So in the classical limit, we have seen that this system is going to have an energy 3n kBt. We have already done this. Hence, so to see whether we go to this limit, what we need to do is to substitute for t to infinity, so that beta, which is equal to 1 over kBt, is small. It goes to 0. Therefore, you see, I can expand the exponential. So I have nh bar omega half 1 plus h bar omega over kBt minus 1 e. Limit of t to infinity, which is going to be nh bar omega half plus kBt over h bar omega, and since my kBt is very large compared to this p factor of half, this is going to be nh bar omega times kBt over h bar omega, which gives me the result nkBt, which is precisely the result for this, because we are looking at a only one-dimensional system. We said in the very beginning that 3 dimensions can be treated independent of each other. So if you just do it for 1 dimension, you can just add in the results. So for a 3 dimension, you are going to have 2 more factors of nkBt coming in, and you will have this. Limit of t to 0 is when this factor, the exponential factor, dominates, because 1 over kBt beta goes to infinity, and you have nh bar omega half plus e to the power minus h bar omega over kBt. Once again, the specific heat now becomes dE dt at constant n, which is nh bar omega e to the power minus h bar omega over kBt times d dt of minus h bar omega over kBt, which is going to be nh bar omega e to the power minus h bar omega over kBt. I have a minus h bar omega over kb, and the derivative d dt of 1 over t, which is going to give me minus 1 over t square. So this is minus 1 over t square. So I have nh bar omega minus h bar omega over kBt. I'm going to have h bar omega over kb t square. Let's recast this a little bit, rearrange, multiply by kb and divide by kb, so that this kb, now I plug it over here to give me h bar omega divided by kBt whole square. So there is one factor of h bar omega, one factor of h bar omega, that gives me this, and I have multiplied with kb divided by kb. So I have multiplied by kb and divided by kb, and this gives me kBt square e to the power minus h bar omega over kBT. So this is going to be your specific heat.